When looking towards a green future, wind energy is one of our most promising technologies. In the past few decades, AEP has taken initiative to be a leader in sustainable energy, especially in the field of wind turbines. From our own calculations, AEP's wind energy can now supply over 800,000 households. When we came across this challenge, we immediately knew this was a project we were going to take on. We combined our passion for data science and for the environment to create a product that everyone can use.
We began our analysis of the data by researching the key components of wind turbines and common failures. Based on this research, we knew it was important to heavily consider all factors, especially changes in the environments and mechanics. Some of the key factors we found essential to our algorithm were wind speed, power output, rotor speed, state and fault, and material temperatures. Using the pandas package on Python, we created smaller usable data sets that filtered out our essential key factors, took random samples of the population data given, and cut out our quote unquote bad data. Using each data set, we could gather a more specific scope on how each turbine performed in our key factors. It was clear that turbines A, B, D, H, I were underperforming based on the reduced capacity factor and time availability compared to the other turbines. In addition, we appended each simplified data set in order to make this interactive graph displayed on the screen in the Python package Streamlit, which was also used to make our website. Although the simplified data sets helped us gather a clearer scope on each turbine's performance, the primary purpose of simplifying these data sets was to incorporate them in our machine training.
Due to the numerous factors impacting turbines, we decided to use machine learning to help predict the health of a turbine. This is our first time working with the scikit library, and we used a variety of models consisting of a random forest classifier, SVM classifier, and a neural network to analyze whether or not a single or set of turbines are faulty based on key relevant numeric factors. Once we trained our model with a sample of 1,500 carefully cleaned data points, we used a truth table to evaluate the accuracy. In the end, our neural network appeared to be consistently superior over the other two models at around an 82% success prediction rate. We then used a random forest classifier to create a model that determines the best location for a wind turbine from a variety of locations using open source wind and weather data. To test this, we compared 3 locations with drastically different wind conditions: New York, Tucson, and Lake Erie. Then we chose a location with the highest true positive healthy turbine rate given from our models. From our sample, it turned out to be Lake Erie at 84%.
Reflecting, one of the biggest challenges was learning how to overcome our minimal Python and library experience, as well as learning how to implement deep learning within the limited time we had. In the future, we'd like to increase the scopes of our projects by improving our location-based machine learning model to handle user inputs of locations or weather and the output projected success of a wind turbine at the input.
Thank you.
Honestly, leave that.